Bismillahirrahmanirrahim. Assalamu alaikum dear students. Welcome to the online lecture on the MATLAB simulations of nonlinear control. Today we are going to discuss this paper, sufficient condition for the existence of the compact set in the radial basis function neural network control. This paper is published in IEEE Transactions on Neural Networks and Learning Systems. It is a good paper. We are not going to discuss the paper in detail, but I will highlight the main contributions of the paper and the major part of the theory that we are going to use in our simulations. So this paper has derived the sufficient condition for existence of compact set for the neural network control of first order systems, and then they have also proposed the condition for existence of compact set for the neural network based backstepping control of higher order nonlinear systems as well. So the example that we are going to simulate today is going to be third order nonlinear system, and that will include backstepping control with the radial basis function neural networks. So let's look at some preliminaries. For any continuous function f of x, the compact set Cx, there exists a neural network satisfying the f of x is theta transpose phi plus epsilon, where epsilon is upper bounded by epsilon bar, and within all the x in the compact set Cx. This means that f of x can be estimated by a neural network, and the type of neural network discussed in this paper is Gaussian basis function, which is selected by exponent of x minus mu j over 2 sigma. Here mu and sigma are constants, and there are these theta, these are the basically coefficients of this phi function, which is a function of x. You can find the optimal value of theta, which minimizes the difference between f of x and the neural network predicted value of f of x. So basically f of x is an unknown function, and neural network is trying to learn f of x. They first discuss the first order system x dot equal f of x plus u of t. F of x is unknown continuous function, and control objective is to make the system state bounded. So they just looking at the boundedness of the state. They just want the state to stay within some compact set. So f of x can obviously be learned by neural network, and there are some properties of Gaussian basis function which are discussed here. M is the number of functions phi that are used in the system. There is some existing control design that u of t, if selected in such a way, then, and also the estimate of the coefficients of neural network are evolving in this manner following this differential equation. Then you can get the semi-globally uniformly ultimately bounded solution. But the problem with this solution, as the authors say in this paper, this is that the set is not is not guaranteed to be compact. So for example, the compact set of first order systems, in this section they say that, so for example, let's say you have c of x. If you have your initial condition within this compact set, then there should be some other compact set c prime of x, which should be preferably be the subset of this c of x, where the trajectories of the state space should lie. So with this type of control, they say that this cannot be ensured. So this is the problem that has been addressed in this paper, where they found the conditions under which basically such kind of things are ensured. First of all, there is some assumption that f of x is, although it is unknown, but it should be bounded by a non-positive f bar in such a way that the absolute value of f of x cannot be greater than f bar by 2. Now remember this thing. We will come back to this when we are writing the code. So I'll just let me just highlight this. Okay, so define a supplementary function like this. So we are not going to go into the details of how they proved the existence of the compact set and everything. We are just going straight to the business, but in order to start our business of simulation, we need to know at least some preliminaries. So this is the control law that they have proposed. U is equal to minus ku x. Ku is a constant, theta hat, that is the estimate of the coefficients. This again is the Gaussian basis function, which is some sort of exponential function. This is the upper limit of the unknown function f. And then they have like this kind of theorem that you have semi-global uniformly bounded solution. Then there are some other there is this one was for the first order systems, and then they propose for the second order systems. For higher order systems, they say that let's assume that the control function meets first of all, they assume that the states are in sort of like integrator chain format, which is basically x1 dot is equal to x2, x2 dot is equal to x3, x3 dot is equal to x4, and the final state, the derivative of final state should be in this form. Xn dot should be f of x plus g of x times u plus d of xt, where g of x is basically multiplication function for control input, d of x is the disturbance, f of x is the nonlinear function which is unknown, but we know the upper bound. So here we assume that we know the upper bounds on this g of x is g1 of x plus delta x, where g1 of x is the known part of this unknown g of x, and this unknown part delta is upper bounded by delta bar g. Then g is greater than g1, and g1 is greater than some constant g1. So g1 of x is known continuous function. These are all the assumptions, and disturbance is also assumed to be less than some constant d bar. Then they for backstepping control, they define some virtual control variables, and then control is designed by this equation. So u of t is equal to this tangent hyperbolic type equations. So this is the control law for higher order systems, higher order nonlinear systems using the neural network. You can see here this phi is the Gaussian basis function. This theta hat is the estimate of the coefficients in the neural network. So coefficients have their own dynamics. Theta hat dot is equal to 0 if the norm or magnitude of theta hat is equal to some constant theta bar, and zn, which is the nth virtual variable, it's greater than 0, or if any of the theta j is equal to 0 and zn is less than 0. All of these conditions we will write in the MATLAB code, and similarly we will write this control law equation in the MATLAB code as well. So continuing in this manner, they discussed different Lyapunov function based proof of their theorems, and here basically that is the section that we are most interested in, simulation example. So in this section they have provided a third order system, x1 dot equal x2, x2 dot equal x3, x3 dot equal to this nonlinear time varying, basically this is a nonlinear time varying function, and in this system f of x is this equation, g of x is also given, and then g1 and different things have been identified. So what we are going to do is we are going to simulate this system in MATLAB. So before we start looking at the code, let's look at different values that are given here. For example, this g1 is equal to 1, delta bar g is 2, d bar is 0.1, and then they have defined z1 is equal to x1, z2 is equal to x2 minus alpha 1, z3 something like this, alpha 1, alpha 2, Then they have defined this control law that we are going to simulate, and the adaptive law that is also going to be simulated in MATLAB. And then there are these neural network based information that phi of x is there are 27 Gaussian basis functions that have been used in this example, and each of the 27 functions is this same equation, x minus mu I over 2 sigma, where mu I is basically it's a vector of 3 values, minus 0.6, 0 and 0.6. so we can have like 27 of these mu ij for every I and j. Sigma is 1, x bar is 0.6, compact set is x such that magnitude of x is less than 0.6, and k theta, gamma theta, these are some constants that are going to be used in the control law. So in order to save time, I've already written the code for this, and let me show you how I have done this. So let's put the paper and the code side by side, and we shall see how this works. So first of all, you have to define all the constants. So gt here, this is the gamma theta. So here this is gamma theta is equal to 1, so gt is gamma theta. Kt is k theta, that is also 1, so this is the value of k theta given here, this is 1. Then s is basically sigma is this sigma, and this sigma is given to be 1 as well, so I have written it is equal to 1. M is equal to 27, so here. And f bar is actually not given in the paper, but I have calculated f bar from a separate using two information. For first information is that x belongs to this compact set C of x, which is from 0 to 0.6, and the second information is the equation of f of x. So remember that f of x, absolute value of f of x cannot be greater than f bar divided by 2. So in order to find f bar, you can use this code. So this is the code for calculating f bar. So you can have x1 from 0 to 0.6, x2 from 0 to 0.6, x3 from 0 to 0.6. Actually these are because f bar only includes the even powers of x1, x2, x3. So I have used x1 square, x2 square, x3 square from 0 to 0.6, and if the square root of x1 plus square root of x1 square plus x2 square plus x3 square, that is basically the norm. This norm has to be less than 0.6. If this norm is less than 0.6, I calculate the value of f of x, and after calculating all the values of, if I run this and I calculate all the values of f of x, and then I just find maximum of f, that is 0.129, and if I multiply this with 2, because remember that maximum of f is f bar by 2, so twice the maximum of f, which is 0.259, I have approximated it to be 0.26. so here, coming back to the code, this is f bar 0.26 or 0.259 would be the same results. So you can calculate f bar from the given data in the paper here, as I have done. You can go to the relevant screenshot of the video, pause the video and copy the code on your own MATLAB and try to run it. That will also give you some feeling. I have to keep the video as short as possible, so don't expect to learn everything just by listening to the video. You also have to copy the code that is presented in the video. So phi max is also going to be used. So here phi max is given by 20.185, which I have copied here. Theta bar is basically the upper limit of theta, which I have taken from here. If you go here, so you can see this is theta bar, and theta bar is square root of m f bar over 2 theta max. So phi max, so phi max is 20.185, so theta bar is square root of m f bar divided by 2 times phi max. So some things are not given straightforward, you have to either search in the paper or calculate by using different code. So f bar I calculated using different code, and this theta bar I had to search into the paper the equation for theta bar. But well, all of these other constants ka1, ka2, ku, these are given in the paper. You can see here this is ka1 is equal to 1.5, ka2 is equal to 2, ku is equal to 2.5, and then mu is equal to 0 minus 0.6, 0 and 0.6. This is given here, and then you can calculate the phi I. Phi I is exponent of x minus mu norm square divided by 2 sigma, which I have calculated in the same way, exponent of minus norm of x. So remember, in our MATLAB the state space will have 30 states. 3 states will be x1, x2, x3, and remaining 27 states will be the theta estimates. So x1 to 3, the first 3 states will be x1, x2, x3 minus which is basically x here, minus mu I is this vector, the norm square divided by 2 sigma square. So that's the code. And then phi is basically all of the 27 phis are same. So and then you go to this product theta. So theta, remember, is the x the state variables number 4 to 30. So theta transpose phi, that is just this product that is being used in the control. So this theta hat transpose phi, this product I have given it because it is used again and again. Then next is z1, a1, z2, a2, these are given here. So z1 is x1, so z1 x1, a1 is minus ka1, so this is a1 minus ka1 z1. The reason I defined a1 before z2 is because a1 is being used in z2. So you cannot write the equation in the of the code in the same manner as they are written in the paper, because paper does not require logical flow, the code requires logical flow. So a2 has to come before z3 because z3 is using a2. So here this alpha 2 here, this is basically a2 in my code, and then there is something, this alpha 2 dot. So alpha 2 dot here, this is being used in the control. So so alpha 2 dot is here. So in the paper the expression for alpha 2 dot is given in terms of ka1 z1, ka1 ka2, all of these things we already know. So we can write this equation here so that we can use later on. So next is let me go to the control equation, and then we look at this z, capital Z, this is this capital zeta, and then dB is the d bar which is given in the paper. So you can write the equation minus ku z3 minus tangent hyperbolic, all this equation you can just copy in the MATLAB, and this is the equation of the control input u, and you can see here that it goes all the way up to this d bar. So and then once you have computed the control, then x1 dot, x2 dot, by the way, this is the value of d bar is 0.1, which we have already written here, dB is equal to 0.1. Then x1 dot is equal to x2, x2 dot is equal to x3, x3 dot is equal to this whole equation. I have just copied it in the MATLAB, and you can see wherever there is t, so I can write this t, because here while defining this function on the top, function dx equal nnbs is my chosen name, so t and x are normally the input arguments of anything that you are trying to solve using the ODE function in MATLAB. So this t you can use here, and then there is a check, because in order to implement this theta hat dynamics, you have to check if there exists a theta which is equal to 0. So I have for j between 4 to 30, if x of j is equal to 0, then check is equal to 1. If check is equal to 1, that means that there exists at least one theta j which is 0, which I need to define the dynamics of this theta hat. So the dynamics of theta hat are defined as, if the norm of this theta is equal to theta bar, as it is written here, and z3 is greater than 0, or if z3 is less than 0 and check is equal to 1, which means there exists theta j equal to 0, then theta dot is all zeros. Otherwise theta dot is this gamma theta multiplied by z3 into phi minus this k theta times theta hat. Theta hat is all these states x4 to 30, and then dx is x1 dot, x2 dot, x3 dot, theta dot. Theta dot is a 27 cross 1 vector, and these are all three scalars, so overall dx is a 30 cross 1 vector. So this is the code for the dynamics of this example. Next is you have to write the code for calling the ODE, like calling the ODE 45 function and implementing or plotting the solutions. So you use tx equal ODE 45 at your name of the function, and I have run it from 0 to 10 seconds, because if you look at the results in the paper, these results are from 0 to 8 seconds. So this is what I want to reproduce here. And then the initial conditions are also given in the paper. So if I look here, so initial conditions for the three states are 0.3, minus 0.3 and minus 0.4, which I have copied here, and initial condition for all the 27 coefficients of neural networks is 0.001, which I have written it 27 times. Here you can see that it's written 27 times, and now and once I calculate the time and the state trajectories, then I can plot them. I can plot the three state variables separately. Let me add the legend here. Legend, you can add legend x1, x2, x3. You can save it. Okay. And then there is in order to reproduce the control law, you have to basically copy this code from here. So this code up to the equation of the control, you have to copy it here. So I have copy pasted it, but the difference is that once I define the constants, the equations are basically these are phi I, phi and u. They are recalculated from the trajectories x. So this I have discussed in the previous video as well, how to do this. So I'm not going to go into the details of this again, but you can pause it, and if you have even a little bit understanding of how the logic of the programming works, you can easily understand how I have This is the little modification that I have done in the code everywhere. So this is xi comma 1, whereas here it was simply x1. You can see here that it was simply x1 to 3, and here it is xi comma 1 to 3, and this is for all I from 1 to length of t. So you calculate u and you run it, and I've already calculated the results. You can see here these are the results, and if you compare with the results in the paper, here are the results of the paper. These are almost the same but not exactly the same. This state from minus 0.4, this goes up and it comes down at, it settles at about 4.5 seconds. Here it also does the same, it goes up and it settles at about 4.5 seconds, but the trajectory is slightly different. You can see here this peak is less than 0.3. Here this peak is between 0.3 and 0.4, and this could happen due to multiple reasons. One of the reasons could be that my ODE solver is different from the ODE solver used in the paper. Second is that I have estimated f bar using my own method. Here this f bar, remember this, I calculated this from using my own method. So I don't know, they have not given the value of f bar in the paper, so that could be some difference, but nonetheless the difference is not too much, because this state from 0.3 comes down, and this again here this is the almost same, and then this state from minus 0.3 goes down a little bit and then goes up, and this same behavior here, minus 0.3 goes down a little bit and then comes up, and I don't have this sharp turn here, so my turn in my simulation result is smoother. Similarly, if you look at the control, here the control is some chattering in the control, and if you look at my control, there are two differences. First of all, the chattering is much more compared to this control, but overall structure is the same, but there's also difference that my highest magnitude of this control is close to 2, and in my case the highest magnitude is 4. Now, having said that, let me show you what happens when I have used ODE 45. Let me see if I use ODE 23S and run this code and see. So I have not changed anything, I've only changed the solver. So you can see already that the difference in control, although the maximum magnitude still remains 4, but overall shape is similar to this. It goes towards the negative side and then comes back to 0, stays close to 0. And then similarly, if I use, let's say, 23 instead of 23S, if I use simple 23, ODE 23, similarly I can try different solvers and then see what happens to the results. And but the overall fact is that that's how you simulate the example given in this paper. It's taking some time to load, to calculate. Let me see, MATLAB is busy, so it's gonna take some time, but anyways, it will keep on running and it will show me the figures whenever it's ready. But this was the lecture, and I hope that it was useful for you. Here this is the code for the MATLAB function, user defined function, that where we have defined all the differential equation parameters and the differential equation that's itself, and this is the file where we call the ODE 45 or 23 function and plot all the data, and this is the function that we used for calculating the f bar, which is the upper limit of f. And let me see if this MATLAB, okay, it's still computing. Okay, so I will once it is ready, I will show you the results. So finally the results are here, and you can see here that again the trajectory is pretty much the same as computed by other solvers, but the control is yet another shape, which is different from what we got from ODE 45 and different from what we got from ODE 23S. And so far, I mean, if you look at the chattering in control signal, the least amount of chattering that we have obtained so far is from ODE 23S. And also ODE 23S takes lesser amount of time, but I mean, taking lesser amount of time does not necessarily means that these are the best results. I personally most of the time I prefer ODE 45. So thank you very much for listening.